Okay, good morning. We are starting a new topic, and this topic deals with the frequency response of cascaded amplifiers. We had discussed the motivation for why we require this. Frequency response. We did not record that lecture, so we'll quickly go over that and then continue on. So this is a topic which you will also come across when you do a course on control systems, but you might see that in a slightly different flavor, but nevertheless I think it's interesting for us to do it here. So the basic idea is the following, that if you want some decent amount of gain, which is, for example, your aim is to make an op amp, right? The aim is to make an op amp. And the op amp has a gain of say 100,000 or something like that. This would imply that you need multiple cascaded stages of amplifiers. Then we saw that each of these stages actually has a frequency response, right? So each stage has a frequency response. And the other important point is that the op amp itself will be used most likely in negative feedback. Right? So you have a situation where I have individual amplifiers, right? Let me call those as amplifier 1, amplifier 2, so on and so forth. Let me say I have 3 stages, correct? Each of them has a frequency response, which is something I am drawing here, just as a toy, right? And this complete set of amplifiers is going to be in a global feedback loop, and that global feedback loop, let me just draw in red, right? So you are going to take all of this, pass it through some return block which I will call B, right? And then say there is a summing junction there, and you are going to give that to the negative side, and this will be the positive side. You will have some V in and you will have some V out. Okay? Yes. There is no speciality. No. See, it will be the same. It's just that when I draw A, I'm visualizing an amplifier. The unit B itself, as we'll see on the next slide, is typically some kind of passive element. It's not an active element, the feedback block, most likely, right? The forward elements are all gain stages. For our purpose, the return stage is, for example, an R1, R2 or an R1, C1 kind of combination. So that's why you can draw it in any way, there's really no problem. Okay? So this is the idea, and what we basically want is to find out, what is V out by V in. Okay? And the important thing about V out by V in that we want to find out is where are its poles? Where are its poles and zeros? And we have to then comment on its stability. Okay, that's basically the goal of what we are trying to do. And in the last class, we also actually had a typical kind of op amp configuration, right, where the B network became very clear. and that op amp configuration was the non-inverting op amp configuration, right? So the non-inverting op amp configuration, I have my V in given directly to the positive terminal of the op amp. The negative terminal of the op amp has feedback there, right? And that feedback here we created using two resistors. We call this resistor having a value of k minus 1 times R, and this one having a value of R, correct? And if we were to map this same circuit to the previous block diagram of something with A and then a feedback block with B, correct? Can you tell me what B is? Right? So this, the feedback path itself over here, right? What is this voltage? Because the current here is 0. The feedback voltage on the negative terminal is nothing but V out into R by R plus k minus 1 times R. This is the voltage that is here, correct? That's the voltage which is being fed back into the negative terminal of the amplifier, and this whole quantity itself is nothing but V out into V out by k. Okay, and if you look here, what is the element which is fed back into the negative terminal? No, B times V out in this circuit, right? V out, B times V out is fed back, right? V out, B times V out is fed back. So you compare that quantity and you compare this quantity, and you come to the conclusion that the fed back quantity, the return transfer function, right, or the backward transfer function is nothing but 1 by k. Okay. Now typically, if I were to take this this block itself, what is my V out by V in? We have done this many times. It is 1 by B into AB by 1 plus AB, correct? And we had defined some quantities over here. What were those quantities? Okay, what were the quantities? We defined a thing called the closed loop gain. What was the closed loop gain? Closed loop gain is essentially what I wrote here. Once you close the loop, what is V out by V in, right? Why should people be confused about that? Which is nothing but 1 by B into AB by 1 plus AB. We also discussed a quantity called the loop gain. What is the loop gain? AB. Loop gain means you start with something over here, right? You go through the loop there, you come here and come here, right? So if I start with X here and I go through this, I will get AB times X, right? That is effectively you have opened the loop, and you are calculating what is the gain because of the forward block and the return block, right? Okay, let me not have that there, it just complicates matters. So that is your loop gain. Okay, also we discussed that the typical usage would require AB to be much greater than 1, in which case your V out by V in is 1 by B. Okay, so your typical usage requires your loop gain to be much greater than 1. Okay, now if I were to just draw this, write the same things out with B being 1 by K, what happens? This is nothing, this is just V out by V in would be what? K times what? No, all the steps. So this will be closed loop, would be K times. So I can write it in another way. I can just divide AB and AB here. So if I'll get K into divided by what? So I'm dividing AB. So I divide the numerator and denominator by AB. So I'll get a 1 by AB plus A plus 1. And my 1 by AB is nothing but is that right? So I have in general I'm saying that this block has a dependence A of S, return block is just B, right? So V out by V in is K divided by 1 plus K plus A of S, is that right? Okay, then yes,
V out by V in
yes,
terms of this situation.
correct,
But if we see only the op-amp, then V out, because this is virtually short negative feedback.
correct.
V in equal to V out by Z.
Yeah, but your op amp is, so the question is, in the op amp itself, what is the relationship between V out and V in? Okay, you can go calculate it. What will it be?
Since V minus is V out by K.
Yeah, but the op amp, before you compare what you get with the op amp and the expression we have written here, remember that the op amp is working with AB, loop gain being greater than 1, right? So you should put that condition here. What is the condition for loop gain being greater than 1? AB greater than 1 is identical to what in terms of K, right? It's A by K greater than 1. Okay, so if your A by K is greater than 1, you get V out by V in being equal to K. Okay, which is what you had. Suppose you had this quantity as equal to say R2 and say this quantity was R1, then what was your V out by V in? We have done this many times, right? It was 1 plus what? 1 plus R2 by R1 times, yeah, it was just this, right? Is this correct? Is this right or wrong? Okay, this is correct. Okay, this was your non-inverting amplifier. Okay, so with this thing as a background, let's go calculate some things. Let's start first with a first order transfer function in a feedback path, in a negative feedback loop. Okay, so what we're going to do is to do first order, then second order. Those two you can do analytically. Then we'll do third order, and then we will see that it's difficult, and so we'll come up with some more general way of doing this. Okay, all right. So what does that mean? So I'm going to take my A of S. I'm going to take my A of S to have this form: A naught divided by 1 plus S by P1, where P1 is greater than 0. Okay, so this whole quantity, where are the poles? The pole is at minus P1. Is it stable? So this block itself is stable, right? Stable A of S. Okay, now let me get the closed loop gain. What's the closed loop gain given by? It's given by, we derived in the previous page, right? It's K divided by 1 plus K by A of S, which would become what? K divided by 1 plus K into reciprocal of this, which would be 1 plus S by P1 divided by A0. Okay, so now this I will approximate in the situation of what? Let me approximate this quantity A naught by K greater than 1. Okay, if I assume A naught by K greater than 1, then this quantity becomes K divided by 1 plus K S by P1 A naught. Okay, so where is the pole of this guy? Pole at minus P1 A naught by K. Okay. Now, is the closed loop transfer function stable? Is this stable? Yes. Why? Because pole is again at, pole is in the left half plane. Okay, does everyone remember what the impact of the position of the pole on various things? Can somebody? So let me assume I have a rational transfer function. What does that mean? Means that you can write the numerator as the form 1 plus s by a1 into 1 plus s by a2, so on and so forth, divided by denominator is of the form 1 plus s by p1 into 1 plus s by p2, so on and so forth. Okay, where all of these quantities a1, ai and pi are all real. That's a rational transfer function, right? Okay. Now let's further consider the situation where you have a situation with only poles. We'll worry about the situation with zeros later. Okay. So you have only poles for now. So what can you say about the poles? Because these are all rational numbers, they should appear as. So you have a polynomial which has all rational coefficients. If I have imaginary roots or complex roots, they should appear as, yes, right? Implies all poles are complex conjugate pairs, right? In general. Okay. So if I have a pole there, I should have a pole. It's not a. So if I have a pole there, I should have a pole exactly here. If I have a pole here, I should have a pole there. Okay. If I have a pole here, no problem. Similarly, if I have a pole here, no problem. Okay. Now, can you help me draw what the response for all of these things is going to look like? Okay. So this response is for these two poles put together. This response is for that pole. Then for these two together, I have one. And here I don't have space, so I'll take this out here. And okay, what response am I interested in? I am interested in the response as a function of time. Okay. First, which one is easy? Okay, let me draw one of them and then you can help me with the others. So if I take this, is this going to be a decaying signal or is it going to be a growing signal? This one, decaying. Is it going to oscillate or not? Think again. There is a real part, right? So it has to have some kind of ringing. So this one will look something like that. Is that right? And the value of the real part will set what is the frequency of this oscillation. The value of the imaginary part will set what is the decay. Okay. Now can you tell me about this one? It will not ring. Okay. And it will be an exponential decay. Okay. Which one will decay faster? This one or that one? See, the one that has larger magnitude of the imaginary part will decay faster, right? So this one should decay slower, right? Because the magnitude of its imaginary part is actually smaller than this. Sorry. Oops, sorry. The one which has a larger magnitude of real part will decay faster. So this one will decay slower. So I'm going to, so if this decay rate was something like that, right? This one is going to decay slower. Okay, it doesn't really look very slow. Let me clean this up. Okay, so this one is going to decay much quicker than that. So we'll first draw the envelope, but then it's going to actually ring and decay. Okay. Now how about this guy? What's going to happen here? How is the envelope going to look for this? The envelope itself will grow with time, and it will ring like that. And what about this guy, the fourth fellow? Okay, and its envelope, the magnitude is smaller, so it will grow slower, right? So if it has to grow slower than this, it might grow something like that. Okay. Is that right? So which of these is stable, which of them is unstable? Right? Okay, so this is stable. This one is, this is also stable, but you have to remember that this has ringing, right? And here, so this is unstable. Why is it unstable? Because things will grow with time. And what is this? This is also unstable. Okay, what is it that we have plotted here? Yes, but a time function is a response to something, right? So what is the input for all of these things? No, step will right? Okay, so I leave that as something that you have to go and think about. What is it that we have? This is the response for some input. What is the input? Okay, think about that. Is it an impulse? Think carefully and come back tomorrow. Okay, we'll clarify that tomorrow. So this is not the step response. It is a response to some time signal. Okay, what time signal is it? So just think about that. Go and read your notes on signals and systems. Okay, so we basically want to be in this region. This is where we want to be, right? That is the left half plane. That is, we want the poles to be in the left half plane. Okay, all right. Here, just to finish this, what happens if I have a signal that is here? What happens if the poles are there? Right? How will that look? What does marginally stable look mean? Sinusoid. Good. Right? So the signal will look so it will basically not die with time. Is that right? Okay, good. So think about what is this the response to. Okay, all right. Okay, with this picture in mind, let's go back to what we had, which was our transfer function, which is of this form, right? Where a transfer function like this. Let's go and plot this guy out and see what we can get out of this. Okay. So this transfer function is your closed loop transfer function, and the transfer function is basically V out by V in is this quantity. Okay, I am just going to massage this a little bit. I will write this as S divided by A naught P1 by K. Okay, and I will remove this K from the numerator. Okay, and we had the open loop transfer function itself. What is the open loop transfer function? A, right? So we maybe should write that down on this page itself. You have a loop gain. Okay, I have written in terms of gain. So closed loop, loop, and open loop. Remember this. Okay. So open loop transfer function is what? Is just A of S, right? And that is nothing but 1 by 1 plus S by P1. Okay, what is it that we should do with these? Okay. A naught by 1 plus S by P1. Okay, what should I do with all of these things? Make Bode plots. Okay, we have already done this, so you can quickly tell me. First we take the open loop case. Open loop case, where should I start with? A naught, right? I should start with A naught. Okay, so where's the pole for this? Pole is at minus P1. Okay, important point that possibly we should clarify here, right? I'll insert a page here. Okay, now I have a pole 0 plot like this, right? And I am drawing frequency response. What is the connection between your pole 0 plot and your frequency response? So I have some pole 0 plot. Let me just clean up stuff that I don't need. Okay. Okay, it's some pole 0 plot. How do I, so I am drawing frequency. What is frequency response? What's on my x-axis and y-axis for frequency response? So frequency response has on the x-axis omega, right? Your poles and zeros are basically what? So as we had, right, we had a, for this particular case we had a function like this, 1 by 1 plus S by P1 into 1 plus S by P2, so on and so forth, right? So this was what we plotted on the pole 0 plot. So if I were to call this as some what's a good letter? Okay, if I call this as V of S, correct? What are we plotting in the frequency response plot? The frequency response, what do you plot? The 20 log and all of that is okay, but what is the essential quantity? V of j omega, right? It's not V of S, it is V of j omega, and you're doing that, right? You plot it on a log scale, you multiply by 20, all of that, that's okay, but essentially you're plotting a quantity which is V of j omega, correct? And you have this pole 0 plot. The pole 0 plot, this is what? Imaginary part of? So this is imaginary part of S and this is real part of S. Okay. So how do you go from the, so how do you connect these two? Radius of a circle, that's correct. But even earlier, even simpler than that, what are you essentially doing? You're basically taking omega along this axis, right? You're taking omega along the, because you're plotting S equal to j omega, which means you're looking only along the imaginary axis, right? And you're looking at the response. That's what you're doing when you're doing the frequency response. So the frequency response is nothing but, this is the response V of S for S along the imaginary axis. That is why these poles, for example, if I call this as P1 and I call this as P1 star, right? This P1 and P1 star will not. So what's a pole? Pole is something that causes V of S to go to infinity, correct? In the frequency response, P1 and P1 star will not give you anything that goes to infinity, because you are not really on that line. You are looking at the response for S equal to j omega. Okay, think about what happens to these poles P2 and P2 star. Okay, how will the response because of poles P2 and P2 star appear? So if there was a system which has poles located on the imaginary axis. That is how I have drawn them as P2 and P2 star. I want you to draw the frequency response. Okay, think about that. We'll consider that again tomorrow. Okay, all right. So this is just so that people later on remember what this page was. What is this page? This is connection. Have you done this before? Okay, good. Yes. Yes or no? Okay, somebody says yes, somebody says no. Okay, so think about this. Okay, so in general, the problem is if I give you a pole zero plot, you should be able to draw the frequency response. That's more complicated. There's a systematic procedure. You will do that in control systems. Okay. All right, let me draw now the frequency response of this guy. Where will my pole be? Minus P1. So where will the corner frequency be? P1. Okay. P1. So until P1, this guy is going to be straight, right? After P1, what happens? It's going to drop at how much? Minus 20 dB per decade. Okay. And what about the phase response? What's it going to start at? So this is the magnitude. This is the phase response. Phase response starts at 0 and ends at what? Think and tell. You shouldn't. How many people say it ends at minus pi by 4? Good. How many say it ends at minus pi by 2? How many say it ends at minus pi? Okay. So it's a first order function, right? So it should end at minus pi by 2. Okay. So how will it look? What about the situation at the corner frequency? Minus pi by 4. Okay. So it will basically be something like this. Go here and then be like that. Okay. This is for, so I am going to keep a key here. That guy is for open loop. All right. Now help me draw the closed loop case. Okay, before we draw closed loop, let us do loop gain. Okay. First let's draw loop gain. What is loop gain? It's just A of S by K, right? So how will that look? It will start at A naught by K. Okay. Where will its corner frequency be? P1. Okay. And what happens? Okay. Phase response you guys will do, right? Okay. So I am not doing the phase response. Alright. What is this quantity? How much is that quantity? Huh? A naught by K into P1. How did you get that? Yes, so you remember that if you go down, right? If you go down some quantity, right? You can basically go to the right by the same amount. Right? And why is that? This is because this function is of the form 1 by S by P1. It's linear in S, right? So how much ever you lose in terms of magnitude, you can gain in terms of the frequency axis. Okay. All right. Now I also want to plot. What's the third quantity I want to plot on this plot? Open loop, loop gain and closed loop. How will the closed loop function look for this? At low frequency, where is it going to start? K, good. And then, okay, this one has to draw carefully, wait. Okay, it starts at K, then it remains flat all the way until what? So you can see this, you have gone from A0, you have gone down to K, which means you have gone down by a factor of A0 by K. So your frequency, the corner frequency which is at P1 should go to the right and should go to the same, should go to A0 by K times P1, which happens to be also this one. So it's actually here, right? So we did all of this in detail on the board in the previous class, which we did not record, right? So I hope you have all, we also did it in the quiz. Is that right? Okay, so now can you name all these quantities for me? What is this frequency called? This frequency is called what? Okay, what are the frequencies I need? I need this frequency, then I want that frequency. Okay, what are these names? This is called the unity gain frequency. Why is it called the unity gain frequency? So I'll call that omega u. So omega u is the frequency at which the closed loop gain becomes, so I'll write it in blue, so it is connected with the closed loop gain. So when the closed loop gain becomes equal to 1, right? This whole thing is 1, right? This thing is 1. The horizontal line is 1. Is that right? Okay. What about this quantity, which I will write in green? Okay. What is this quantity called? So it's called the loop gain unity frequency or unity loop gain frequency. And what is that designated as? Omega u loop. Okay, all right. Now just look at, I'm not drawing the phase response, but you can very easily draw it. Maybe we should just draw it for completeness. What will happen to, we'll draw it only for the closed loop function. For the closed loop function, what will happen? This will be pi by 4, right? So this whole thing will just get stretched a little bit. Right? So that will be the phase response for the closed loop function. Okay, what has happened now to the bandwidth? Okay, so I am going to look at open loop and closed loop. Okay, and what are the quantities I want to look at here? Let me look at DC gain. Okay, let me look at bandwidth. Okay. So what's the DC gain for this guy? And open loop, let me write with red. So DC gain is A naught. Closed loop DC gain is K. Okay, what's the bandwidth of the open loop case? P1. Okay, what kind of bandwidth is this? 3 dB bandwidth. Why is it called 3 dB bandwidth? Because the mod squared, right, goes down by a factor of 2, right? Okay, this is open loop is P1. What's closed loop? A naught into P1 by K. Okay. Okay. So what did we conclude from these two? Right. Okay. So from this we concluded that the gain bandwidth product for a first order system is constant. Okay, that is valid only for a first order system. Don't generalize to higher things. However, there are some things which are general, and for that I am going to take this to the next page, and with that maybe we will be done for today, and I will give you an exercise for tomorrow. Okay, now we are looking at this quantity. Okay, now look carefully at the loop gain. Okay, which is the loop gain? Okay, look carefully at the loop gain, which is your green line. Okay, and look at the closed loop transfer function, which is the blue line. And can you comment on this? Remember your V naught by V in itself, right? How did you write this as? In the general form we wrote it as 1 by B, AB by 1 plus AB, and your AB is nothing but your loop gain. So this is nothing but 1 by B, right? And maybe your 1 by B is essentially K. So it is K into loop gain L of S divided by 1 plus L of S. Right? Okay. Now can you take two limits of L of S being greater than 1 and the other case where L of S is less than 1, and tell me what happens to these two cases. So in this case V naught by V in becomes equal to K, and what happens to this case? Think again. When loop gain is less than 1, okay, KLS is nothing but what? A. Right? So K is 1 by B, L of S is AB, so K times L of S is A. Okay. So what does this tell you? What does this situation where L of S greater than 1 mean? Okay, tell me, I'll give you a word, I'll give you a noun, give me an adjective for it. Okay, I want you to tell me how much of feedback is there in the system. Okay, so amount of feedback is the quantity. Tell me high or low. Okay, so in the case of L of S being greater than 1, is the feedback high or low? High, right? Because how does this thing look, right? There is a block, forward block, backward block, and it's coming in like this, right? So that is your B and this is A. Correct? So L of S greater than 1 means you are taking a lot of this output and you are feeding it in there. Correct? So okay, so L of S greater than 1 corresponds to high feedback. What about this case? L of S less than 1. So it's almost identical to no feedback. Right? Okay. Now with these two, Can you now look again at the green line, blue line and red line and understand what's happening? Look first at the high feedback case. Okay, look at the high feedback case. So at the high feedback case, loop gain greater than 1. Where is loop gain greater than 1? So it's below the unity loop gain frequency, that is here. Is that right? Right? Greater than 1, I have converted it to greater than 1. Okay. In the situation where you have loop gain greater than 1, you have a high amount of feedback. Right? And in that region, look at what is your final closed loop quantity. The closed loop quantity is K, right? So what is happening there? So it's essentially the same thing we have written down in words. I am just trying to allow you to see it pictorially, because what will happen is, for higher order transfer functions we can't do these things analytically. You will have to look at the graph and then determine what's happening. Okay, so what's happening here? For quantities, for the frequency at which loop gain is greater than 1, that's what I have highlighted in yellow. You see that the closed loop transfer function, right, is constant. Correct? So that's when you have feedback, and that's when your amplifier is operating the way you want. When the amplifier is operating the way you want the gain to be K. Correct? When the feedback is on, you want the gain to be K, and that is happening provided your frequency is less than the unity loop gain frequency. So this unity loop gain frequency is a very, very important quantity. When your frequency is less than the unity loop gain frequency, your amplifier, the feedback is decent, and so your feedback system operates the way you have designed it to operate. Okay, what about situation when your frequency is greater than the unity loop gain frequency? So that I am going to do in another color, maybe green. Okay, so where is that? That is here, right? And what's happening there in the green region, or actually further even, right? All of this. In that region, what is happening? What have you seen here? Your quantity, right? So all of this is for what? All of this is for the closed loop. So the closed loop quantity becomes equal to K, right? So the closed loop quantity becomes equal to K in the case of high feedback. It becomes equal to the open loop situation when you don't have any feedback, which is reasonable, right? So when your loop gain is very poor, it means that basically you are not feeding anything back, which means the existence of this B block is immaterial. So whatever you get as the closed loop transfer function is essentially going to be equal to your open loop function, which is exactly what you are seeing. Beyond the unity loop gain frequency, your loop gain is dropping below 1, correct? Loop gain becomes less than 1, that's the green line. In that region, your closed loop function, which is the blue line, identically follows the open loop function, which is the red line. Okay, so what's the take home from all of this?
I have to operate the amplifier only in the
So the unity loop gain frequency exactly determines the bandwidth of the closed loop transfer function. Is that right? So I want all of you to go and review this particular bit of information again. It's very important. For subsequent cases, when we look at higher order transfer functions, we will not be able to draw all of these things very cleanly. However, this point will be still valid. That is, for unity loop, for frequencies less than the unity loop gain frequency, your closed loop transfer function is determined only by the only by the feedback part, which is here k. And for frequencies greater than the unity loop gain frequency, the transfer function is completely determined by the open loop function, alright, which is a. Again, completely determined, you have to take with a pinch of salt. We are drawing it in the Bode plot sense. However, so all of these transitions are not going to be very precise, they will be smoother. However, the general trend is identical, right? That is, if you want your system to have feedback, you should work at a frequency less than the unity loop gain frequency. If you work at a frequency greater than the unity loop gain frequency, you will not have any feedback. Okay, all right. So that completes what we want to do for the first order case. I am going to just leave this as an exercise for you for the second order case. I want you to calculate these things and come. Okay, assume your A of s is of the form 1 plus s by p1 into 1 plus s by p2, okay, where p1 p2 are greater than 0 and real. I want you to calculate the closed loop function. Also, I want you to write the closed loop function denominator. You write this closed loop function as the form of a numerator and denominator, right? I want you to write the denominator of the following in the following form: s squared plus 2 what? 2 zeta omega n. You remember this form, right? For a second order function, omega n s plus omega n squared. Or if you divide everything by omega n squared, what will you get? You will get s squared by omega n squared plus s into, correct, right? This will become 2, right, plus 1. And what can you say about how is quality factor related to zeta? You have done this. So you replace this by q. Where will your q come? So this quantity can also be written as s by what? S by q. Okay, so I want you to calculate the closed loop function, write it in the form of numerator by denominator, and from that determine what my omega n and zeta are. Okay, work in the limit of so determine omega n and zeta in the limit of what limit? Sorry, this is a naught. Limit of a naught by k greater than 1. Okay, so this is second order. Please do this so that we can continue from here tomorrow. All right, thank you.